I'm in the process of repairing and restoring an HP9845B vintage computer. I am making a bit of progress, and in this video I'll show you some of the faults I've found and discuss what I intend to do about them. Before we get into that, I just want to answer a couple of good questions that came up on the previous videos. The first was how I keep track of all the bits and pieces, screws and bolts and boards and parts that I take off these. Now, I'm not saying that the way I do it is the best way to do this, but this is something I've been doing for a long time, so I've kind of developed a method of keeping track of all bits and pieces. Bear in mind that I only video a very small proportion of the repairs I carry out. It's just a few machines that I show on camera. But I do a lot of repairs, and some of the repairs can take weeks or months to complete. So there's bits and pieces hanging around for a very long time. So I like to try and keep track of them. Also, because I'm working on so many different pieces of equipment at the same time, it's important that I keep track of which parts came off which machine. If I start mixing them up, then all bets are off, and things can go horribly wrong if I end up with the wrong part in the wrong machine, especially if most of them aren't mine. So I don't want to start swapping over other people's bits and pieces. So the first thing I do is I have a rack of these plastic drawers. I've got several racks of these plastic drawers. I use some for keeping components in, but one particular rack I use as a project rack, and so for each piece of equipment I start work on, I create a drawer, and this is used for current operations, so to speak. So when I'm working on something such as the chassis, this will contain all the screws and nuts for that particular part of the machine, and that enables me to keep track of what's going to be fitted for a particular part of the assembly. And a machine like this it's a bit like an artichoke. You kind of start peeling it from the outside, and as you delve deeper into it you remove more parts, but you don't really want to start mixing those parts up. So on larger projects like this, where you end up with bits and pieces, I use one of these. So this particular project, I've actually got two of these on the go, so there's quite a lot of parts come off this. And you may have noticed in some of the video shots, and I show things like this, the strange numbers that may appear on some of the bits and pieces, in this case 1766. Now 1766 is the project number, and it's on everything to do with the project. As I say, this might be hanging around in pieces for months or even longer. So on the front of each bin, I've got several hundred of these bins and some storage racks that they fit into. So on the front of each one is a piece of A4 paper folded in half. On the outside is the project number, and on the inside, where it's folded over, are just notes for the project, tell me what the current status is, if it's waiting for parts, that sort of thing. But in the actual bin I keep all the parts. Many are numbered, so if it's parts, for example, so these are the chassis bolts for this particular project. If I'm going to reassemble the chassis, I'll put these into the current bin, and that enables me to make sure I'm using the right screws. So that's basically all the parts for this machine. As I said, I've got two of these bins, but it also includes things such as the boards. If I remove boards, they go into a protective bag and into the bin, along with all the other parts and bits and pieces. If the part's too big to fit into the bin, such as the top cover for this machine, then what I do, if I can find it, is I fit a tag. So this will have a tag with the project number on. Now this may seem like a lot of trouble to go to, but it really does not take very long, and it can save you a lot of time trying to find parts that, if you lose a part, and especially if it's not your machine, bear in mind a lot of the parts on these are irreplaceable, then it can save you a huge amount of time and cost by not losing things in the first place, and this only takes a few minutes to do. Also, what I do is any information that I've gathered for the particular project I keep in the bin with it. This will ultimately go into a folder, a ring binder, when I finish the project, so I'll have some historical information if I get another machine the same that needs work, and you kind of build up a library of information, which is why the repairs tend to get easier over time, because I'll have some historical information to refer to on machines I worked on in the past. If new information comes up as I'm working on a machine that I've worked on before, that will go into the particular ring binder. So for example, I have a ring binder for this particular machine. I've worked on about 5 or 6 of these in the past. I've never owned one before, and so I have a ring binder. There isn't much in it because most of the repairs were fairly easy, so this is the first time I've had an in-depth dive into one of these, and it is quite interesting. But this is how I keep track of the parts. The second question was how I hook up the logic analyzer to the machine, and how do I connect it to the ROM, how do I connect it to the CPU cards. Now on the CPU card on this particular machine there is a test connector, but how I hook these up varies depending on what's available. So on this machine there's an edge connector. I can put one of these. This is a wire wrap socket, so you take the wire wrap socket, we've got the pod out of the logic analyzer, and then these will just push onto the wire wrap pins on the socket. So they're quite a nice fit, and this is really what these are designed to fit onto. So these are a perfect sliding fit on here. They're properly spaced, of course, so they're 0.1 pitch, so you can just put these all the way along if you want to, and that makes it very easy. If I want to transfer the connections from the LPU on this machine to the PPU, because the pin out on the edge connector is identical, I can just unplug this without disconnecting the logic analyzer connections, move it across to the other side of the machine and plug it onto the PPU, and that's it. Literally takes 30 seconds to transfer from one side of the machine to the other. Different machines, different solutions. I usually end up making up some sort of adapter to fit onto the various machine if it's got a particular format for the edge connector. If you watch my series on the 9830 repair, you'll see I made up several different types of adapters and connectors when I was working on that. So again, you build up quite a collection and they go into the bin. The other thing I do when I'm working on a particular project is once I've hooked up the logic analyzer pods, I tend to leave them connected. So for example, if I want to connect to the ROM on this machine, then I've already got everything connected. I've got about 100 of these pods, so I'll leave them connected to, in this case, a test clip. The test clip will clip straight onto the ROM, of course, and this saves me a lot of time hooking this up. If I want to look at the ROM, all I do is I find the correct one in the project bin, if there is one. If there isn't one, I assemble one, and then once I've got it, all I need to do is clip this onto the ROM, plug it into the appropriate pod connections coming from the analyzer, and then we're good to go. So I can hook one of these up in 30 seconds once I've got the project underway, and that saves a lot of time. Again, it might sound like a long-winded way of doing things, but it just requires a few bags that you can reuse, some tags, and a few minutes, but those few minutes are a few minutes very well spent, because it can save you a lot of messing about trying to find parts that you've misplaced, and especially if you come back to a project after you've had to wait for maybe 6 weeks for some parts. It's nice to know exactly where they all are. Okay, so I'll get the bench cleared up, and we'll get on to the project and see what progress I've made. So if you recall from the previous video, we had the logic analyzer hooked up to the 9845, and when it was trying to boot up, the PPU was not branching to the correct code. It's supposed to branch to an address that takes it to the monitor program, and that is at 7A1E, but it was never going there. It was just going round and round in circles and never going to the correct address. So it looked a bit like it wasn't able to see the signal coming from what should be the monitor. This is the CRT monitor, and I traced that signal through, and it was going directly through to the PPU hybrid pin. As I said, there were some issues initially with that, and I'll post the issues I found with the hybrids in a separate video. But once I'd resolved that and I knew the signal was getting to the hybrid, it still wasn't working, it still wasn't jumping. It was as if I couldn't see the incoming signal. And the only thing that could really be was that it was just not running the right code. And sure enough, when we went through with the logic analyzer and looked at the code that should be running, we found that there were errors in the values being read from the ROM. This is quite a complex setup in terms of how the buses work and the interaction between them. So there are two buses, the X and Y bus. The PPU ROM RAM card sits on the Y bus, and the LPU ROM RAM card sits on the X bus. And normally they, for the most part, run independently, so they can access ROM at the same time. But at boot up, they're both trying to access the block 5 ROM, and so there's some quite complex arbitration circuits to make sure that they can't clash and fight over the access to the particular bus they're trying to use. So there could have been a fault in those circuits, and it was preventing the data from coming back correctly. But I did try a few simple tests just to see if that was the case, and I looked at the signals on the logic analyzer and the scope, and there was no contention on the bus. I was just looking at the access requirement, that's basically what amounts to a bus request and bus acknowledge signal, and looking at those, it was clear that there wasn't really any contention. The LPU card got access to the bus when it wanted it, and the PPU got access to the bus when it wanted it. Incidentally, I don't know if I've mentioned this previously. I think I did, but I may have edited it out. On the right hand side of the machine, the processor card, that's the one with the heatsink, is the LPU, and the processor card on the left of the machine is the PPU. But the PPU RAM card is the one on the right side of the machine. That's the one we've got in this riser. So the PPU ROM and RAM card is actually plugged in next to the LPU, and the drawer on this side is for the LPU. And the RAM card on the other side of the machine that's plugged in next to the PPU is the LPU RAM card. So just be aware of that if you're working on these. Also, somebody asked me how I went about desoldering the ROMs from these boards, and the answer is I didn't. These, although it doesn't look like it, they're actually in sockets. They're like socket pins, individual pins that HP used. So you can just unplug them, they're not actually soldered in, which obviously makes life a lot easier. Unfortunately, the DRAMs are soldered to the board, and I know I've got a couple of faulty DRAMs. But if you do come across one of these, don't try and unsolder them. They're plugged in. The only thing is, they're quite tricky to get back in, and be very careful you don't bend any pins on the ROMs when you take them out, otherwise you'll really struggle to get them back into the sockets, and be really careful when you refit them. But it does make life a lot easier. Now, as you can see, some's already been here before us, and some of these ICs have been swapped. I also think there's still some other failed ROMs, but I found that the ROM was faulty. I took it out eventually, checked everything else, took the ROM out, read it, and sure enough it has some faults in it, so there are some incorrect values in there. So I don't have a replacement. I needed to come up with some way to test this. So as you can see, I've put together a ROM replacement. So all this is really is I needed a 64K ROM, so that was easy, just a 2764, and I programmed it with the code that should be in this. They're in pairs, so this ROM and the one that I swapped out one pair, so they form the lower and upper 8 bits of a 16-bit value, and it's just the upper one that seemed to have an issue. So this board is just effectively one of these. Now we can't just use an EEPROM and change the pinouts, because these ROMs have got a latch on the address inputs, and that means we have to include some latches. So that what we've got on the board is the EEPROM, the 2764, And again, there are only really two choices for the latches. We need a transparent latch. We can't use an edge-triggered latch. An edge-triggered latch would not allow enough time for the ROM to set up the data when the device is effectively selected, because the HP reads the data pretty much as soon as it lowers the chip select line. So the data already has to be available. So we need transparent latches. With a transparent latch, the inputs are passed straight through as long as the latch line is in its kind of high state, and that data then appears at the inputs, the address inputs to the ROM, and then when the device is selected, the HP takes that line low. It not only enables the output of the ROM, but because the ROM by now has had time to select the correct data, and the lowering of that line is also connected to the latch latch control line of the two latches, and that effectively latches the data and prevents it changing when the bus value then changes. Bear in mind we've got a multiplex bus. So the only real options were 573s or 373s. So I've gone for the 373s simply because I had some, and so they are octal transparent latches. So what we have are two of those, because there are 13 address lines and each one of these is 8 bits. So we've got two of those latches and the 2764 EEPROM, and that's what's on this board. I've got it hooked up in a way that should work, and in theory it should work. This board should work exactly the same way as the original ROM. The only problem is, because this machine is actually quite sensitive to noise, and I don't have the printer in, and for some reason with this machine, if you don't have the printer in, the noise is much worse on all the buses and data lines. So I think we're still getting a problem because of that. The machine still won't boot up, but it does get further. So I'll move the camera pointed at the logic analyzer, and we'll see what the machine now does with this arrangement. Before we do that, we can see the scopes. I'll turn the HP on and you'll see the data. This is looking at one of the address lines going into the buffers, the latches on our pseudo ROM. And previously, when I powered up the machine or reset it, there were just a couple of pulses and then it stopped because the code kind of branched off into no man's land and it stopped working properly. But now when I turn this on, notice we're getting continuous activity, so that's completely different. Remember this pattern, and what I'll do now is I'm going to unplug the signal coming from our little breadboard that supplies data through to the PPU when it starts up. So that's now unplugged. I'll power this back up, and if you look at the scope you'll see that the pattern we're seeing is different. So it's now a different pattern. I don't know if you can tell the difference, but it's now gone into this mode. This is the kind of the fault mode it goes into. So again, remember this, I'll plug the our little board back in and you'll see this change. So that's plugged back in. I'll power the machine back up, and you can see it's now different. The pattern we're seeing is settled down into a completely different pattern. So we know it's doing something. We know the PPU is now reading this. And as I say, previously this just died completely after a few cycles because the code wasn't going where it was supposed to. What we'll do now is we'll have a look at the analyzer, capture some data and see how far through the boot up we're getting. Previously it got to the two tests, the two SHC lines, and because it's looking for a high value on the Holt line, this is the PPU, and we're hooked up to the PPU. Although we've got the ROM card on the riser here, the analyzer is connected to the left hand of the two processors. So because this signal it's looking at is the vertical drive signal for the monitor, it should be low 1 millisecond every 17 milliseconds. So about 19 times out of 20 the machine, the PPU should jump straight through, and when it gets to this point it should jump through to this address at 211, and then every so often it will encounter the low period of that signal, it will wait 4 milliseconds and then it will try again, and it should always, if that signal's present, end up jumping to address 211, just sometimes with a 4 millisecond delay. Okay, I'll move the camera, we'll look at the analyzer and see what we're now getting. The operation of the machine has changed slightly. Previously I could press the stop key and it would put the machine into its halt or reset mode. And now pressing the stop key alone doesn't do anything, which is more how it should be working. What you should have to do is press the control key and the stop key at the same time. And that is indeed what you now have to do. So I'm going to do that. We'll arm the analyzer, I'll then release the control key and we should capture some data. And as you can see, we've captured some data. If we now start scrolling through that, again we've gone to bank 25, that's the diagnostic ROM. It's not fitted, so we go through address 21, and then ultimately we should end up at address 200, which is the start of the code. So we're now at 200, and if we look at the code, then we should see a value of 7118, and the 71 is coming from our new ROM assembly, so if that's present we know it's working to a certain extent, and as we can see we are getting 7118. If we keep going through, address 202, we're getting 33FE, and that is again correct, we're getting 33FE. We'll scroll down to the first of the SHC tests, and that's at line address 207. So what we should see there is a value of 7DCA, and we were seeing 79CA, so we'll see what we're getting this time. I'll just scroll across until we find address 207, that's 204, 205, 207. This is now address 207, so let's see what we're getting there. And we are getting 7DCA instead of 79CA, so that is now looking a lot better. That's the correct value, so 7DCA is what we should get. And as I said previously, with the faulty ROM we got 79CA, which was the wrong instruction. If the halt line was low at that point, we should actually now jump through to address 211, so we'll see what happens. It is possible, of course, that it encountered the 1 millisecond low, so 211, and we're getting an address of 7A1E, so we have successfully jumped to the monitor. So we went to 211, we saw the correct value of E90C, I don't know if I showed you that, so E90C, and then that resulted in a jump to the monitor program. So we went to 211, that had a value of E90C, which is the correct instruction, and then that resulted in us jumping to the monitor, and that's at 7A1E. So we'll see if we are processing the instructions there, 7A1E, 7A1F, 7A20. So we are now starting to run the monitor program. The machine still doesn't boot up. I know there are other faults, I know there are RAM faults, I know there are faults with the buffer, I know there are faults on the CRT display board. But we are now at least getting the PPU to branch into its monitor program. So that's a good step forward. We found a fault with the ROM, and there are also some faults with the some of the buffers. If I do a single capture, you'll see these spikes. This is the output of our latch, but the problem's not caused by our latch. If I move the probe across to the input to the ROM, so this is the address, or one of the address inputs, and we do more single captures, this is the signal we're getting, so there's something very wrong going on that bus. Now, it is entirely possible this is caused by us having this board on a riser, and this assembly here is obviously not going to be helping. I don't think that is the case, but it could be. Now, unfortunately, with this arrangement I can't plug the card back in to test that. So the next step really is I need to make up a small module that effectively replaces the ROM. To be a small board, I need to try and find some surface mount devices, I can't use a 2764. It's bigger than the entire footprint we have available. But I'll try and find something that I can make a replacement ROM from, and then we can start replacing any faulty ROMs. I'll also go through, unplug all the ROMs, because this could be a faulty ROM, one of the other ROMs being faulty. I'll unplug them all, see if they all work, verify them, make sure they've got the right coding, and go from there. But big step forward. Machine still won't boot, but at least now the PPU is jumping to the monitor program.